Welcome back to our lecture on Java. We are still looking at OOP, and today we are looking at part 3 of it, which is very important for someone who wants to look into the design part of OO. How can you implement good design? What are the guidelines you need to follow? And all that. So we are going to look at OO design principles and the guidelines to implementing the dependency inversion. So we have a couple of design principles that we are going to look at. The first one being encapsulate the paths that vary. The second being favoring composition over inheritance. Then program to an interfaces, not implementations. Strive for loosely coupled design. Classes should be open for extension but closed for modification. Depend upon abstractions, not concrete classes. Then lastly, the Hollywood principle. Don't call us, we will call you, to avoid dependency rot. So we're going to start with the first one and do a practical presentation of it. Encapsulate the parts that vary. So what we are going to do, the approach is that first we demonstrate the problem and then we demonstrate the solution to it. If you don't encapsulate the parts of your application that varies. So I already have these classes prepared so that the video doesn't take long. We have a drone class here, and as we can see, this drone class can do few things. Obviously a drone can fly, we can display something from a drone, we can have some other additional behavior. But for the purpose of being succinct, we don't want to talk about many things for brevity. So now this drone class is abstract, and it's inherited by a couple of other drones. For instance, we have an aerial drone, we have an attacker drone, and we have now I can just remove all this from aerial drone class for demonstration purposes. Then we have a car drone, we have a Mavic fighter drone, all these things will come back. We have a tank drone. So let's say we wanted to add fly behavior to a drone. What we would do, the easiest thing would be we can add a class void and say fly. Then drone can fly. And then we run this class. Now everything is fine. The problem with this design is that for a tank drone, a drone that does not fly, or we can even say a car drone, not fly. If we run this code, it means we have a unintentionally added fly behavior to a car drone, but that was not the intention. So we see that adding fly to a drone class gives fly behavior to other drones that we don't want to give fly behavior. And another thing, that's the first problem. Another problem is that this fly behavior can change. We can have a drone that flies with propellers, a drone that does not fly with propellers, like a jet drone. You know, we can have different kinds of behaviors. Now, when we have it like this, we are, if we want to change this behavior here, we are going to have unintended side effects to many other classes that implements the drone, extended drone class, and we don't want that. So now we can solve this problem in, especially the first one, the one where we say we don't want to give fly behavior to other drones. What we could do, we could remove this fly behavior here. Obviously we're going to have an error here, and okay, say okay, we have flyable and we have fly method. Then we say okay, only the drones that fly will implement this fly behavior, flyable interface. Okay, Matic fighter, we can say implement flyable. Obviously it will implement that method. Then we go to attacker drone, it also implements flyable. We can also go to aerial drone, it implements flyable. But the problem with inheritance is that if we add some additional behavior to this flyable interface, it means now that we are stuck again. We have a maintenance problem. Imagine all those flying drones, if there are even more than 3 that we have, like let's say even more than 20, we are going to have to modify each single one of them. So that doesn't solve our problem either, as we can see. So we are going to remove this flyable from our Mavic drone. So what should we do? The first solution that we can do is the first principle that we are talking about. It seems that this fly behavior changes often. So what can we do? We can encapsulate that behavior and say flyable. And then what can we do? We can now say public void perform fly. Then we can say flyable.fly. We are done. Now, aerial drone, it does not need to, what we can do, we can give it a fly behavior in its own class. What does the fly behavior, what fly behavior does it have? So this flyable, since it's an interface, we must implement different kinds of behavior. We mentioned that other drones can propel, others they don't use propellers, and others they don't fly at all. So we see we have propeller drones, we have drones jet drones that don't use propellers. Then we have drones that are not flyable, that do not fly at all. So as you can see that in not flyable we are doing nothing. In propeller we say propeller. In jet we can put jet. We are fine. So what we want to do now is that each individual drone we are giving it its own behavior. We can start with aerial drone. So what we need to do is that in a constructor we say flyable. Okay, so in here we can make this protected. So that we say flyable equals to new jet drone. Then we go to attacker drone. It uses propellers. This one we say. Then we say flyable equals to propeller, sorry, new propeller. We go to card row. Card rows, they can't fly, so what we'll do here, not flyable. Then we have Mavic Fighter. Mavic Fighter, it uses a propeller as well to fly. Tank drones. The tank drones, they do not fly. So we are done. So the design that we have here is that we have encapsulated the fly behavior, because this fly behavior varies a lot, and that now has given us many benefits. One of the benefits that is giving us is that we do not cause unintended side effects to classes that we do not want to touch. That's the first one. Another one is that we are also going to reuse code. Every class has the behavior that it needs, and we don't have side effects to other code, and we can add additional behavior without having to even touch the drone class. That's another importance. So now when we come here, if we have a drone, we can just say cat drone perform fly. So let's run and see. Nothing happens. So what does that mean? This means that this drone cannot fly. If we put, let me just say drone. If we put, we say it's an aerial drone. Sorry, aerial drone. This one can fly. We see that it's a jet. It can fly. If we put attacker drone, we see that it's a propeller. It can't fly. So we see now that what we have essentially done, we have encapsulated what varies and separated away from what stays the same, and then we are able to reap the benefit. This is the first principle. The second principle says favor composition over inheritance. So if you see what we are doing with this drone class, we are not inheriting behavior here. We are composing behavior. So imagine if, as I mentioned, that each drone was implementing the flyable, and we change flyable. It means all other classes have to change. So inheritance create those tightly coupled classes that once you change one thing, you have a lot of things to change. That's the problem with inheritance. It doesn't give you that that flexibility or loose coupling between high level and low level components. So always favor composition over inheritance. You could have said implement flyable. So if you implement flyable, it means all other drones, as you can see, must now provide an implementation for that method. Just see what we just added one line, see how many classes are affected. Many classes affected. So if we remove this and compose it, we don't have a problem. That is the second principle. Favor composition over inheritance. Another principle says program to interfaces, not implementations. Program to interfaces, not implementation. So let's see what that means. We have a class, we can close all these things here. We have a class called animal. This animal makes sound. And what we can do is, let me just come here. For the purpose of testing, I'm just going to copy this class into here. So we have a class called animal, and this animal can make sound. And on top of that, animals are of different types. We have a cat, we have a dog. We see that a dog can bark and a cat can mew. So now we are saying program to interfaces, not implementations. If we come here, I'm going to show you the first example of programming to implementation. You can say dog. We can say dog equals to new dog. And then we say dog.sound. So we see that dog.sound. Okay, what is happening here? Dog. Why does it say propeller? Something is not right. I see why. We are running the wrong method, so we have to run this main method. Rather, we have the dog barks, as we can see. But the problem is that if we want a new kind of animal while using the same variable, we are stuck. We can't say cat here because we are coding to an implementation. So what we need to do here, we need to say animal dog equals to dog equals to dog. We can say animal here equals to dog, and we run our code. We get back. We can change it and say cat. We have new. Or if maybe we don't want to change it here, we can later on say animal equals to new dog. We get the new behavior. So this is what we call your coding to an interface, not to an implementation. Now let's say that we wanted to give animal behavior, but not this way. We want to encapsulate behavior because we saw the benefits of encapsulation. Okay, we want to say sound. Sound is an interface. Sound. And what we do is that here we just say sound, and we say sound dot let me see. Can just have sound here. word sound. New back. Then in here we say sound dot sound. And we have encapsulated this behavior. So instead of having cat like this, we now have our constructor. In our constructor we say sound equals to new mu. We are giving our cat a mu. Then we can say sound dot sound. Then we do the same for dog. Then inside animal, just say perform sound, or maybe make sound. Then in our thing we say make sound. We still get the same behavior. So what we have done here, we have also coded to an interface, because if we say we put back here, we put an implementation as opposed to putting an interface, and we come to our own class, it means now we cannot assign sound to some other thing. We are stuck, because now in the animal we make it to be back. Hence now we are not coding to interface, we are coding to implementation. It always has to be an interface. That's another principle. So now we want to also review classes. We saw that strive for loosely coupled design. We saw when classes are closely coupled with inheritance, the problems of code change that they escalate to many other classes. We have already seen that one. Then now we want to look at classes should be open for extension but closed for modification. Let's review that principle. So let's say that we have a car and we have a bucket, we have a sedan, we have SUVs. And now let's create a car. Maybe we can say Wrangler. We know that Wrangler is an SUV. And it can actually use off-road. So what we need to do here is, this is fine. Then we can add, which other one? We can add Toyota Starlet. Toyota Starlet, a sedan. Okay, maybe for now this is fine. And then you also happen to have a main method in here as well. I'm just going to remove this, which is our testing method. So in this main method, what you need to do is that we can have let's just say we have etol for now, or toll gate. Then inside the toll gate we have public void determine route. We are giving it a car. So what we want to do is, this is the last toll gate, and you to go to your destination address, you have two options. You have off-road, just for the purpose of the demonstration. You have off-road, you have tar road. If you use tar road, you're going to take like 200 kilometers to reach your destination. If you take this one off-road, you're just going to take 50 kilometers to reach your destination. So based on the car that you're driving, we have to decide whether you off-road or you take a tar road. We know that we have okay, maybe I can remove the backcase for now, just so that I don't have a lot of examples to work on. We have a sedan, is a car. We have an SUV, is a car. Then this car, what we can do, so that means that if what we can do in this tollgate method, we are going to have if statement. If car maybe instance of SUV, what we want to do, we want to say off-road. If car instance of sedan, what do you want to do? Tar road. So in your main method, we are creating a car here. So what are we going to create? We say Wrangler equals to new Wrangler. Then we have tollgate. Then we say tollgate dot determine Wrangler. We see there that okay, we have to run it like this, sorry. we see that it takes off road. If it was okay, I'm just gonna say car here, car, let's say Toyota Starlet, tar road, because it cannot go off-road. So now I want to create another kinds of cars, vehicles, another category. Let's say it's a truck. And then we create another truck. That truck, we call it we can say Volvo 8 truck, extend truck. So now we have to come back to it all now to make another determination to see if car is a truck. Okay, let me go. A truck is a car, sorry. That's why it was not working. If car is a truck, take off-road. We see that when we add new kind of a truck, we always come and do some changes to the toll gate class. That means this principle is broken. Our class is not closed for modification. It's open for modification while we are doing some extension to the application. So what we need to do is to prevent this scenario where we need to always check this and do some other things. So the question now becomes, what should be the solution to avoid this? That we are extending our class and we have to do modification on other classes. There is a better way to prevent this problem. So now if we come here before we even go there, we say Volvo 4 truck, we run it. It says off-road because it's a truck. So what we need to do, we need to come into our car class and say, okay, public void, we can say determine route. So this method can be abstract. Determine route. Then we can also have this as abstract, because an SUV is then abstract. Then we have truck abstract. What else? Sedan, SUV, truck. So now each individual one of these must now determine a route. Say, okay, I'm a Wrangler. Come here, where is the okay, we remove that. So what we need to do as a Wrangler, sysout off-road. The Wrangler, Toyota Starlet needs a tar road. Volvo truck, off-road is fine. So now what we can do in here, we remove all this. Just say car.determine route. We are fine. So now if we run our code off-road, if we say Toyota Starlet, the sedan, the tar road, say Wrangler, off-road. So now we can even add other types of cars and other types categories, maybe a buggy, and a buggy is a car. Abstract. Then what kind of buggy we have? We can have let's say we have Suzuki buggy, Suzuki 331 buggy. It's a buggy. Then what we do, we know that buggies support off-road. Then when we come to our main method, just say Suzuki, we run our code, it's an off-road. We see that for this code to work, we didn't have to come to the toll gate and make some changes. So that's the same principle we are trying to do. Our class is open for extension but closed for modification. Then let's go to the next principle. Dependency inversion principle. Depend upon abstraction, not concrete classes. I think in a way we have already touched this, but let's see. So let's say we have class A, which depends on class B. Class B is just implements di, or what we, for now, let's remove this. We see that class A depends on B, depends on a concrete class. And we have already seen that that has many problems. So let's just do this. And then I'm just going to remove this code and remove this one. We have main class. We have di. So what we can do now, we can say, and what we want to do, we want to say AA equals to new A. So what we can then add here is a constructor, the purpose of demonstration, which means now we have to add the new B in here. This is fine. So now let's say that this B here, okay, let me just say B is a bed. So we have a bed here. or we can even say B is N. It's not a bet, it's a daf, sorry. So that means we put a daf here. This should be a, sorry guys, I didn't think through this one. This should be a bet. So what we are doing here, we are saying A is a daf, and we have this, and we put a daf here, which is fine. Let's say now we want to add some other kinds of bet, like can say equal. So now let's say bet. This should ideally be a class extending bet. It's fine. I'm just doing this for the purpose of the demonstration. So we see that A depends on daf T. But now we want to invert our dependency. What we can then do is, instead of putting daf here, we can put bet. We can also put bet here. So what we essentially here, we have inverted our we have applied what we call inversion to the dependency, and we are moving away from the concretion, which is the concrete implementation. We are coming to the abstract thing, and this we have seen how this helps us. It's important that if we now want to use a different kind of a bet in A, not just a daf or maybe an equal inside our main, we can also put equal here. That's the importance of dependency inversion. It opens those up for us. Then last but not the least is the Hollywood principle. Don't call us, we will call you. So in a way, we have already explained that one. So this Hollywood principle says if a class is depending on some other class, it doesn't need to create that class. Rather, it doesn't need to call it to create it. The class that is being required must itself be the ones that comes to the class. So what we are essentially doing here, we are creating object A and we are giving it equal. That's what we mean by Hollywood principle. We are passing the dependency to the class. The class does not need to have the responsibility to do the creation itself. We are passing it a dependency. And we see this in many frameworks like Spring. It's called inversion of control. That the class does not create dependencies. The dependencies themselves, they are created somewhere and they are brought to the class. That's basically what we mean by don't call us, we will call you. As we see here in A, we have this dependency and we are passing the dependency to it. But we could have done something like this. And this is not what we want to do. We want the dependency to be created outside and passed to us. So with Spring, a container does that for you. It creates dependency and injects them into where they are needed. Then we are done with the OO design principle. Lastly, guidelines to implementing dependency inversion. No variable should hold a reference to a concrete class, as we saw that the variable that you put there should not be daft, it should be bad. It should not hold a reference to a concrete class. Number 2, no class should derive from concrete class. That's another principle for dependency inversion. Just depend on interfaces. One of the things you will realize with Spring Framework, so many interfaces. And an interface is the underlying foundation for dependency inversion. So by all means, strive to not derive from concrete classes. Then lastly, no method should override an implemented method of any base class. If you have a base class, maybe it's an abstract and it has implemented that method, your subclass should not override it. It's a principle in a way. Although maybe you can say we always do that all the time, but the principle for dependency inversion says no method should override an implemented method of any base class.